The design for a water plant's generator installation presents several critical issues related to safety and compliance with the National Electrical Code. The primary concerns revolve around the transfer switch installation and the lack of appropriate overcurrent protection, grounding, and service entrance considerations. Firstly, the absence of overcurrent protection at the transfer switch is a significant hazard. The transfer switch itself is not service entrance rated and lacks any internal overcurrent protection devices. This configuration allows the potential for excessive current to flow into the building in the event of a fault, posing a considerable safety risk. Secondly, the overhead service drop connects directly to the transfer switch without passing through any overcurrent protection devices. This means that a fault in the overhead line could result in a hazardous current flowing directly into the building's electrical system. Thirdly, the existing 400 amp disconnect switch lacks a grounding conductor. This lack of grounding creates a potential safety hazard, as dangerous voltage could accumulate on equipment within the building. Finally, the automatic transfer switch lacks a manual disconnect for the incoming normal power. This makes it difficult to safely service or maintain the equipment. These design choices lead to several National Electrical Code violations. NEC Section 230.95 requires service entrance conductors to be protected against overcurrent. In this design, the service entrance conductors lack this protection. NEC Section 250.24 mandates that all services must have a grounding electrode system. The existing 400 amp switch does not meet this requirement. NEC Section 700.15 specifies that all transfer equipment must be service entrance rated, which the specified transfer switch is not. NEC Section 700.16 requires transfer equipment to have the ability to disconnect all ungrounded conductors from all sources. The current design lacks this capability due to the absence of a disconnect. It is difficult to reconcile how the designer could interpret these code sections to allow for this design. The code requirements are generally clear, and there appears to be little room for subjective interpretation on these fundamental safety issues. To rectify these design flaws, several corrective actions are necessary. 1. Install overcurrent protection devices at the transfer switch. This could involve using a circuit breaker or a fusible disconnect switch rated for the full load of the building. 2. Reroute the overhead service drop through overcurrent protection devices. This could be achieved by installing a meter main combination or a dedicated circuit breaker in the building's main electrical panel. 3. Install a grounding electrode system. The system would need to be designed and installed in accordance with NEC Article 250. 4. Install a manual disconnect switch ahead of the transfer switch. This would provide a means to disconnect the incoming normal power for service or maintenance purposes. In summary, the design as described presents significant safety hazards and code violations. Addressing these issues through the recommended corrective actions is crucial to ensuring a safe and code-compliant electrical installation. The absence of overcurrent protection at the transfer switch is a critical flaw. Overcurrent protection is designed to protect electrical systems from excessive currents which can result from short circuits, ground faults, or overloads. Without this protection, a fault in the system can lead to overheating, fires, and equipment damage. A service entrance rated transfer switch typically includes built-in overcurrent protection or provisions for installing it. The absence of this feature in the specified transfer switch is a major deficiency. The direct connection of the overhead service drop to the transfer switch, bypassing any overcurrent protection, exacerbates this issue. Overhead service drops are exposed to various environmental factors and potential hazards such as lightning strikes, fallen tree limbs, and vehicle accidents. These events can cause surges in current or voltage that can damage equipment and create safety hazards. Overcurrent protection devices, such as surge arresters and circuit breakers, are designed to mitigate these risks. By omitting these devices, the design leaves the building's electrical system vulnerable to damage from external events. The lack of grounding at the existing 400 amp disconnect switch also raises serious safety concerns. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to quickly trip and energize the circuit. Without proper grounding, fault currents can flow through unintended paths, such as metal enclosures or equipment frames, creating a shock hazard for anyone who comes into contact with them. The NEC Article 250 provides detailed requirements for grounding and bonding electrical systems. Complying with these requirements is essential for ensuring electrical safety. The automatic transfer switch's lack of a manual disconnect for the incoming normal power poses a challenge for maintenance and troubleshooting. In situations where the normal power source needs to be energized for repairs or inspections, a manual disconnect allows personnel to safely isolate the equipment. Without this disconnect, it may be necessary to shut down the entire building's electrical system to perform maintenance on the transfer switch or related equipment. This can be disruptive and inconvenient, especially in critical facilities such as water treatment plants. The NEC violations identified in the design underscore the importance of adhering to established safety standards. The NEC is a comprehensive set of guidelines for the safe installation and operation of electrical systems. It is developed and updated regularly by experts in the electrical industry to reflect the latest technologies and best practices. Failure to comply with the NEC can result in fines, legal liabilities, and, more importantly, increased risk of electrical hazards. The recommendation to install overcurrent protection devices at the transfer switch is a fundamental requirement for electrical safety. Circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a predetermined level. They are available in various sizes and ratings to protect different types of equipment and circuits. The selection of appropriate overcurrent protection devices should be based on the load requirements of the building and the ampacity of the conductors. The recommendation to reroute the overhead service drop through overcurrent protection devices is another critical step in mitigating potential hazards. This can be achieved by installing a meter-main combination which combines the functions of a meter socket and a main circuit breaker in a single enclosure. Alternatively, a dedicated circuit breaker can be installed in the building's main electrical panel to protect the service entrance conductors. The recommendation to install a grounding electrode system is essential for providing a safe and reliable ground fault path. A grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are connected to the building's grounding system. The grounding electrode system must be properly sized and installed in accordance with NEC Article 250. The recommendation to install a manual disconnect switch ahead of the transfer switch provides a means to safely isolate the equipment for maintenance and troubleshooting. A manual disconnect switch can be either a fused or non-fused type. A fused disconnect switch provides overcurrent protection in addition to the disconnect function, while a non-fused disconnect switch only provides the disconnect function. In conclusion, the design issues identified in the water plant's generator installation pose significant safety hazards and code violations. Addressing these issues through the recommended corrective actions is crucial to ensuring a safe, reliable, and code-compliant electrical system. It is imperative to consult with a qualified electrical engineer or contractor to ensure that all work is performed in accordance with applicable codes and standards. The initial concern revolves around the absence of overcurrent protection directly at the transfer switch. According to the NEC, specifically Section 230.95, service entrance conductors must have overcurrent protection. The intent here is to immediately protect the building's electrical system from faults originating outside the building. Since the transfer switch isn't service entrance rated and lacks built-in overcurrent protection, this requirement isn't met. The existing overhead service drop, connected directly to the transfer switch, creates a vulnerability. External factors like lightning or damage to the overhead lines could lead to high fault currents entering the building without any immediate protection. This can damage equipment and pose a fire hazard. The lack of grounding at the existing 400 amp disconnect switch, as per NEC Section 250.24, presents a shock hazard. Grounding ensures a low impedance path for fault currents, allowing overcurrent devices to trip quickly. Without it, fault currents can travel through unintended paths, like metal enclosures, potentially electrifying them. The automatic transfer switch lacking a manual disconnect makes maintenance dangerous. A manual disconnect allows the building to safely isolate the switch from the utility power, crucial for any repairs or inspections. Without it, shutting down the entire building's power may be the only option. Corrective actions must be taken to address these safety concerns. Firstly, install overcurrent protection at the transfer switch. This could be a circuit breaker or fuse disconnect rated appropriately for the building's load. Secondly, we route the overhead service drop to pass through overcurrent protection before reaching the transfer switch. This could involve a meter main combination or a breaker in the main panel. Thirdly, install a grounding electrode system following NEC Article 250 to ensure proper grounding for the building's electrical system. Fourthly, install a manual disconnect switch upstream of the transfer switch for safe isolation during maintenance. Ignoring these issues isn't an option. The NEC exists to ensure safety, and these violations create real risks of fire, equipment damage, and electrical shock. The NEC states under 230.95 that service entrance conductors must be protected against overcurrent. The described design fails to provide this protection at the transfer switch. The transfer switch, lacking service entrance rating and overcurrent devices, makes it non-compliant. The service drop connecting directly into the transfer switch exacerbates the problem, leaving the building vulnerable to faults. The NEC Section 250.24 also says that all services must have a grounding electrode system. However, the existing 400 amp disconnect lacks proper grounding, again violating the code. Furthermore, NEC Section 700.15 states all transfer equipment must be service entrance rated, which is not the case here. NEC Section 700.16 goes on to state that transfer equipment must have a means to disconnect all ungrounded conductors. The automatic transfer switch lacks this disconnect. The designer's interpretation of the code allowing this design is questionable. The NEC requirements for service entrance protection, grounding, and transfer equipment are clear and unambiguous. To fix the issues, firstly, overcurrent protection must be added at the transfer switch, either with a breaker or a fuse disconnect. Secondly, the service drop must be rerouted through overcurrent protection devices like a meter main. Thirdly, a proper grounding electrode system should be installed per NEC Article 250. Fourthly, a manual disconnect switch must be installed before the transfer switch to isolate power for maintenance. The absence of overcurrent protection at the transfer switch means that in the event of a fault on the utility side, there is nothing to limit the current flowing into the building's electrical system. This could lead to a fire or explosion. The direct connection of the overhead service drop to the transfer switch, without any overcurrent protection, further increases the risk of a fault on the utility side, causing damage to the building's electrical system. The lack of grounding at the existing 400 amp disconnect switch means that if there is a fault to ground, there is no low impedance path for the fault current to flow back to the source. This could result in a dangerous voltage buildup on metal parts of the electrical system, posing a shock hazard. The automatic transfer switch's lack of a manual disconnect means that it is not possible to isolate the transfer switch from the utility power supply. This could make it difficult to perform maintenance or repairs on the transfer switch. The design as it stands violates several sections of the NEC. The primary violation is NEC Section 230.95, which requires that service entrance conductors be protected against overcurrent. The design also violates NEC Section 250.24, which requires that all services have a grounding electrode system. Additionally, the design violates NEC Section 700.15, which requires that all transfer equipment be service entrance rated. Finally, the design violates NEC Section 700.16, which requires that transfer equipment have the ability to disconnect all ungrounded conductors from all sources. The designer's interpretation of the code is incorrect. The NEC requirements are clear and unambiguous, and there is no room for interpretation on these issues. To correct the design, the following actions must be taken. Firstly, overcurrent protection devices must be installed at the transfer switch. Secondly, the overhead service drop must be rerouted through overcurrent protection devices. Thirdly, a grounding electrode system must be installed. Fourthly, a manual disconnect switch must be installed ahead of the transfer switch. The design must be corrected to comply with the NEC and to ensure the safety of the building's electrical system. The main issue is the lack of overcurrent protection on the line side of the transfer switch. The NEC is very clear in section 230.95, which requires overcurrent protection for service entrance conductors. The second issue is lack of a grounding electrode system. The NEC is clear in section 250.24, which requires a grounding electrode system. The lack of a disconnect for the service conductors is another issue. The NEC is clear in section 230.70 that a disconnecting means shall be provided. It is difficult to see how the engineer thinks this design is compliant with the NEC. This design has several issues. The first and most important issue is the lack of overcurrent protection. The second issue is the fact the switch is not service rated. The third issue is the lack of a grounding electrode system. The design should be changed to add overcurrent protection, use a service rated switch and add a grounding electrode system. The code sections being violated are 230.95, 250.24, and 700.15.